What if you could take the most advanced quantum processor Google has built, put it inside a laboratory cooled almost to absolute zero, and ask humanity's oldest question: who built the universe? Imagine the screen going dark, the machine running calculations no ordinary computer could reproduce, and then an answer appearing that seems to point beyond mathematics and into the structure of reality itself. That story has been circulating online, and it sounds like one of the most important scientific discoveries ever made. But there is a problem. The real experiment is stranger in a completely different way. Google's Willow quantum processor was never publicly documented as being asked who built the universe. There is no verified secret experiment showing Willow receiving that question and producing a message from another dimension. No peer-reviewed result proving that the machine detected a cosmic creator. And no scientific evidence that quantum computers can retrieve information from parallel universes. What Google actually demonstrated is still astonishing. Willow contains 105 physical qubits, achieved a major breakthrough in quantum error correction, and performed a specialized benchmark computation in less than 5 minutes that Google estimated would take a leading classical supercomputer around 10 septillion years. The result was real. The universe question is philosophical. And that distinction creates a much more interesting story, because once we separate the verified science from the viral fiction, Willow brings us to a question that physicists genuinely struggle with. If mathematics can describe the universe with extraordinary precision, where do the rules themselves come from? Humanity has been asking that question for thousands of years. Long before anyone had a particle accelerator, a radio telescope, or a quantum processor, people looked upward and tried to make sense of existence itself. Ancient civilizations explained reality through creation stories involving gods, cosmic forces, divine beings, primordial waters, or battles between supernatural powers. Greek philosophers gradually moved in another direction, searching for principles that could explain nature without requiring every event to be the immediate decision of a deity. Thinkers argued about whether reality was made from a few basic substances, whether change was fundamental, and whether the universe had always existed. Thousands of years later, science replaced many mythological explanations with mathematical ones. Gravity could be written as an equation. Electricity and magnetism could be unified mathematically. Space and time became part of a single relativistic framework. Quantum mechanics then revealed that reality at microscopic scales behaves according to rules that contradict ordinary intuition. Every successful theory gave humans another piece of the mechanism, but one mystery remained stubbornly outside the laboratory. Science can increasingly explain how the universe behaves, but that does not automatically answer why there is a universe at all. An equation can tell you how a system evolves once the equation exists. It cannot, by itself, establish why that equation is the law governing reality. That distinction is exactly where the philosophical question begins. And it is also why the idea of asking a quantum computer who built the universe sounds so irresistible. People imagine that because quantum machines operate using the strange rules of physics, they might somehow be able to access deeper truths about those rules. But that is not what quantum computing does. Quantum computers are machines built from physical systems that obey quantum mechanics. They do not stand outside reality looking in. They are part of the universe they are trying to compute. That fact is essential to understanding what Willow actually is. Google announced Willow in December 2024 as its latest quantum processor, developed by Google Quantum AI. The chip contains 105 superconducting qubits. A traditional computer stores information in bits represented as 0 or 1. A quantum computer uses quantum systems in which information can be represented through quantum states and combinations of possibilities known as superpositions. Entanglement allows qubits to display correlations that have no classical equivalent. But the popular description that a quantum computer simply tries every answer simultaneously is misleading. Quantum algorithms use carefully designed operations and interference so that certain results become more likely while others cancel out. The machine does not magically explore every possible universe and then return the best answer. It performs a quantum computation. That computation still requires an algorithm, an input, measurements, calibration, error management, and classical interpretation. Willow's most important achievement was not mystical, it was engineering. Quantum states are extremely fragile. Tiny disturbances can destroy useful information. As the number of physical qubits grows, keeping the computation reliable becomes harder. Google's researchers demonstrated that their error correction system could actually improve as the encoded system became larger. That is a major milestone because practical quantum computing requires logical qubits, whose information survives, despite the physical imperfections of individual qubits. In Google's Nature paper, a 105-qubit Willow processor implemented a distance 7 surface code whose logical error rate was below the physical threshold, required for scalable error correction. The reported logical memory lasted more than twice as long as its best constituent physical qubit. This was the breakthrough scientists were actually celebrating. Not a message from the cosmos, not an oracle, error correction. And in quantum computing, error correction is everything. That may sound less dramatic than a machine answering the oldest theological question, but it is actually more consequential. Imagine trying to build a computer in which the information you're processing naturally wants to disappear. Imagine every calculation generating a probability of error. Now imagine that you need to perform millions or billions of operations while continuously protecting the logical information from physical noise. A conventional computer can use redundancy, error-detecting codes, and stable electronic components. Quantum systems require a different approach. Google's Willow experiment showed that increasing the number of qubits used in an error-correcting code can reduce the logical error rate instead of making the system worse. That is the threshold researchers had been chasing for decades. Once quantum error correction becomes scalable, the door opens toward machines capable of computations that would be impractical for classical systems. That does not mean today's machines can suddenly solve every problem. They cannot. It means the field has demonstrated one of the conditions necessary for future fault-tolerant quantum computing. The distinction is enormous. A prototype does not equal a finished technology. Willow is not a universal machine capable of answering every question humanity can invent. But it is a genuine step toward machines that could eventually model complex quantum systems, chemistry, materials, and other problems where quantum effects matter directly. That is the real revolution. And it is precisely because the technology is real that fictional claims about cosmic messages become dangerous. A genuine scientific breakthrough creates a perfect environment for exaggeration. People take a real machine, attach a real benchmark, add a philosophical question, and suddenly the story becomes Google's quantum computer discovered who created the universe. The original facts are real enough to make the invented part sound plausible, but a scientific instrument does not become an oracle simply because its underlying physics is difficult to understand. The benchmark that made Willow famous was called random circuit sampling. Google reported that Willow completed a specific benchmark in under 5 minutes that it estimated would require approximately 10 septillion years on one of the world's fastest classical supercomputers. That number is so enormous that it exceeds the age of the universe by an incomprehensible amount. But there is an important caveat. This was a benchmark designed specifically to demonstrate quantum computational performance. It is not equivalent to solving a useful scientific problem in 5 minutes that would otherwise take billions of years. The task was chosen because it is extremely difficult for classical systems to simulate as the circuit size grows. Google used it as a test of whether the quantum processor could operate in a regime beyond practical classical simulation. In other words, Willow's performance demonstrated a computational advantage on a specialized benchmark. It did not establish that quantum computers can solve arbitrary problems faster than classical machines, and it certainly did not show that Willow can access information unavailable to the physical universe. Classical algorithms and hardware can continue improving. The exact comparison also depends on assumptions about memory, implementation, and computational resources. Google itself described this result as part of a continuing journey toward useful, large-scale quantum computing, not as the arrival of a machine that can answer metaphysical questions. So where did the who built the universe? Where does the story come from? It appears to have grown through online videos and speculative articles that blended real details about Willow with an invented scenario. One widely circulated video describes researchers secretly staying late in a laboratory, disabling logging systems, asking Willow who built the universe, and receiving strange recursive symbols supposedly revealing hidden cosmic architecture. Another version claims the machine generated patterns resembling error-correcting codes, Fibonacci structures, and the 8-dimensional E8 lattice, then somehow used those patterns to prove that the universe was designed as self-repairing code. None of those events are supported by Google's published Willow research. The Nature paper does not describe such an experiment. Google's official announcement does not describe it. There is no verified dataset, laboratory transcript, technical paper, or reproducible experiment demonstrating the alleged universe answer. This is not a minor missing detail. It completely changes what the story means. If a machine genuinely produced unexplained mathematical output containing evidence of a cosmic designer, that would require extraordinary documentation. Scientists would need to publish the input, algorithm, raw output, statistical analysis, calibration controls, independent replications, and alternative explanations. They would have to demonstrate that the pattern was not generated by the software, not embedded in the training or decoding process, not produced by noise, and not selected after the fact because it resembled a familiar mathematical structure. None of that exists for the viral Willow story. What exists is a real quantum processor and a fascinating benchmark. Yet the fictional story accidentally touches a real scientific debate. One of the most profound questions in modern physics is whether information is fundamental to physical reality. Quantum mechanics describes systems using mathematical states, probability amplitudes, and information about possible measurement outcomes. Black hole physics raises deep questions about whether information can ever truly be destroyed. Quantum error correction has even revealed surprising mathematical connections between information storage and the geometry of spacetime in certain theoretical models. Researchers have discovered that techniques originally developed to protect quantum information can resemble structures appearing in theories of gravity and holography. This does not mean the universe is literally computer software. It does not mean someone wrote reality in a programming language. It means information has become a powerful conceptual tool in fundamental physics. That distinction matters. Scientists are allowed to ask whether reality is computational in some deep sense. Philosophers are allowed to ask whether mathematical structure is more fundamental than physical objects. Cosmologists can investigate whether the universe has boundary conditions or whether multiple universes are possible. But none of those hypotheses becomes an established fact merely because a quantum computer uses qubits. A quantum processor is a physical experiment, not an all-seeing window into the metaphysical structure of existence. The same confusion appears around the word multiverse. Google's Willow announcement noted that its benchmark performance lends itself to discussions of multiverse interpretations of quantum mechanics and cited ideas associated with David Deutsch. But even Google's statement does not say Willow accessed another universe. In quantum theory, the multiverse interpretation is one interpretation of mathematics, not an experimentally confirmed parallel world that scientists can communicate with. Deutsch famously discussed quantum computation in ways connected to many worlds reasoning, suggesting that the computational speed of quantum mechanics might be understood naturally if one considers the existence of parallel branches. But that is an interpretation of why quantum computation works, not evidence that a quantum processor is opening portals into alternate universes. A quantum computer can exhibit interference and entanglement without sending information to a separate civilization in another reality. The mathematical formalism does not give us a radio channel to alternate timelines. This is exactly the kind of subtle distinction that viral science stories erase. They take an intriguing interpretation, treat it as confirmed physics, and then add an extraordinary conclusion. The result sounds profound because every individual word is associated with real science. But the connection between the words has been invented. What about the idea that Willow's output somehow revealed code underlying the universe? Here, too, there is a real concept hiding underneath the fiction. Mathematics describes physical systems with incredible success. The constants of nature appear in equations. Symmetries determine which interactions are possible. Conservation laws impose constraints on what can happen. Quantum field theories represent particles as excitations of underlying fields. General relativity describes gravity through the geometry of spacetime. To a human observer, this can look almost like a programming language. But looks like code is not evidence of a literal programmer. The universe being mathematically describable does not tell us whether mathematics is discovered or invented. It does not tell us whether physical law is a property of reality, a consequence of deeper principles, or something that emerges from structures we have not yet identified. Physicists can search for deeper theories, but they cannot simply ask a quantum chip to output the author of those laws. A processor computes what its algorithm asks it to compute. It does not possess independent access to metaphysical truth. And that brings us back to the question itself. Who built the universe? There are several logically different questions hiding inside that sentence. Who assumes an agent? Built assumes an act of construction. The universe assumes that the universe is an object that existed separately from whatever created it. But perhaps the universe was never built in the ordinary sense. Perhaps time itself began with the universe, making the word before physically undefined at the earliest boundary. Perhaps our current theories are incomplete. Perhaps there was an earlier cosmological state. Perhaps our universe is one region of a larger multiverse. Perhaps the laws of physics emerge from a deeper mathematical structure. Perhaps the universe requires no external creator at all. Science does not currently know which answer, if any, is correct. The Big Bang model describes the early evolution of the observable universe from an extremely hot, dense state. It does not by itself identify an ultimate cause of existence. Cosmological models can explore inflation, quantum cosmology, bounce scenarios, eternal inflation, and other possibilities, but no current experiment has identified a cosmic designer. The most intellectually honest answer from a machine should therefore be, the question is outside what the available evidence can establish. That may sound disappointing, but it is actually profound. A truly advanced scientific system should know the boundary between computation and knowledge. Give Willow a quantum circuit, and it can execute the operations. Give a quantum algorithm the right problem, and it can produce measurement statistics that classical systems may struggle to reproduce. Give it raw experimental data and the proper software, and researchers can analyze correlations. But if you ask a physical processor a philosophical question for which no empirical data set exists, the machine cannot manufacture evidence from nowhere. It may generate a plausible language response if paired with a conventional AI system. It may produce a mathematical output if you define a computational encoding. But the answer's existence would not mean that the universe itself had spoken. The distinction between generating text and discovering truth is one of the most important lessons of modern AI. A machine can produce a compelling sentence without possessing evidence for that sentence. It can discover a pattern without knowing what caused it. And humans can easily mistake complexity for meaning. The real Willow story offers another reason for humility. Quantum computers are extraordinarily difficult to operate precisely because quantum states are sensitive to noise. Google had to engineer hardware, fabrication, control electronics, measurement systems, calibration procedures, and sophisticated error correction algorithms to make the processor behave reliably. The 105 physical qubits are not 105 perfect logical bits from a science fiction machine. They are fragile quantum systems that must be carefully controlled. The Nature research demonstrated a logical memory using many physical qubits and showed that increasing code size could suppress errors below threshold. That achievement is one of the foundational pieces required for future useful quantum computers, but it also illustrates a broader principle. Advanced computation requires extraordinary engineering. The machine is not escaping physical limitations. It is learning how to manage them. This is precisely why the idea that Willow secretly crossed into another reality is so implausible. Everything about the actual research shows engineers fighting carefully measured physical errors, not receiving mystical information from outside the system. And yet, the universe itself may still be stranger than the fictional story suggests. Quantum mechanics already forces us to abandon many classical assumptions. Particles are described through probabilities. Measurements affect what can be observed. Entanglement creates correlations that cannot be explained by ordinary local hidden variables. Quantum fields permeate space. Vacuum fluctuations exist even where no ordinary particles are present. General relativity tells us that gravity is not simply a force acting through space, but a consequence of curved spacetime. The combination of quantum mechanics and gravity remains unresolved. Physicists still do not possess a fully accepted theory that describes both at the deepest level. That gap is enormous. Somewhere inside that unresolved problem may lie answers to questions we currently cannot formulate. But the path forward is experiment, mathematics, observation, and theory. Microscopes reveal cellular structures. Particle accelerators expose fundamental interactions. Gravitational wave detectors let us detect distortions in spacetime. Quantum computers could eventually let us simulate quantum systems that are impossible to model efficiently with classical machines. Imagine accurately modeling complex molecules, new materials, strongly correlated quantum states, or processes occurring inside extreme physical environments. Those capabilities could change chemistry, medicine, material science, energy technology, and fundamental physics. A machine that helps us understand how nature computes itself may ultimately be far more transformative than a machine that pretends to know who created nature. That is the twist hidden inside the viral question. The machine does not need to be an oracle to be extraordinary. Willow has already done something genuinely difficult. It demonstrated that quantum error correction can improve as a system becomes larger. That is not the answer to the origin of the universe. It is an answer to a different human problem that may be almost as fundamental for the future of computing. Can fragile quantum information be protected well enough to make large-scale quantum computation practical? Google and independent researchers are still working toward that goal. The result, published in Nature, is evidence that the field is making progress, not evidence that a cosmic intelligence has been contacted. The real mystery is still open. All right. A programmer can create software that contains no human-readable statement about the programmer. A biological organism can obey physical laws without carrying a direct message about where those laws came from. Even if reality had an external cause, that cause might be inaccessible from within the system. Or perhaps what we call cause does not apply at the beginning of time. These are philosophical possibilities, not established conclusions. The mistake is to assume that a machine capable of very complex computation automatically gains access to every category of truth. The machine has boundaries. Humanity has boundaries. Science has boundaries. And those boundaries are not failures. They are what make the next discovery possible. The most exciting part of modern science is not pretending that every mystery has already been solved. It is discovering exactly how much remains unknown. Google's Willow is a perfect example. In one sense, the processor seems unbelievably powerful. It completed a specialized benchmark in minutes that Google estimated would overwhelm classical computation for a timescale vastly longer than the age of the universe. In another sense, Willow remains incredibly limited. It cannot independently formulate a theory of everything. It cannot determine the meaning of existence. It cannot prove the existence of a creator. It cannot open a portal to another universe. It cannot tell humanity why the laws of physics exist. Those questions remain outside the evidence, but Willow can help create the tools that eventually move the boundaries. That is how every scientific revolution works. The telescope did not answer every question about the cosmos. It made new questions possible. The microscope did not reveal the meaning of life. It revealed cells. The particle accelerator did not reveal the purpose of existence. It revealed particles and interactions. Quantum computers may not tell us who built the universe. They may help us understand the universe well enough that the question itself changes. Perhaps we will discover that the earliest universe emerged from a quantum process. Perhaps we will find evidence of a deeper cosmological structure. Perhaps multiple universes exist. Perhaps the laws of physics emerge from something more fundamental. Perhaps none of these ideas survives experimental testing. And perhaps the final answer will remain unknown. That uncertainty is not terrifying. It is the reason we keep looking. So when you see the headline claiming that Google's quantum AI was asked who built the universe and respond with a mysterious mathematical message, remember what actually happened. Willow is real. Its 105 qubits are real. Its quantum error correction breakthrough is real. Its benchmark performance is real. The difficult engineering is real. The philosophical question is real. The alleged secret conversation with the universe is not supported by the evidence. Perhaps that makes the story even more compelling, because humanity's oldest question is still unanswered. But for the first time, we have machines capable of performing calculations that once seemed completely beyond our reach. Not machines that can speak to the Creator. Machines that can help us understand creation. Not machines that can look outside reality. Machines built to explore what reality can do. And somewhere between quantum mechanics, mathematics, cosmology, and philosophy, the question remains waiting exactly where it has always been. Why is there something instead of nothing? Why these laws? Why this universe? And if there is an answer, will humanity discover it through a telescope, a particle detector, a mathematical proof, a quantum computer, or something that has not even been invented yet? Will we eventually discover that reality has no builder at all? Or will science someday uncover a deeper structure that makes the universe look less like an accident and more like the inevitable consequence of a rule we have not yet understood? Nobody knows. And no honest quantum computer has answered it. Not yet. The extraordinary part is that we now possess machines powerful enough to ask better questions. That is what Willow really represents. Not the end of the mystery, the beginning of a new way to investigate it.